Greetings, children. We're going to be looking at some more stuff with functions. So I just called this video More Functions. And yes, you are in algebra because we'll need it. It's one of my favorite memes, even though it's not really a meme. It's not really even that funny. It kind of always cracks me up. Remember, we're teaching you how to organize your thoughts, not just what to think, how to think, or what to do, etc. We're trying to teach you how to organize your thinking. That's really what algebra teaches you. And just, excuse me, just as a quick note, something we can briefly review, take a look at this mapping right here. This mapping represents a relation, but it is not a function, because look at that zero. Zero is being used twice. So this is not a function, by the way. So it actually wasn't the best choice of cutesy image to put on my first slide. Okay, recall please that a linear function is one whose graph makes a line. So if I take the points that match up x and y, or f of x and x and f of x, if I match up the points on the graph, it makes a straight line. You can tell if a function, rule, or an equation is linear if the equation contains both x and y, or at least y. And please remember, f of x and y are interchangeable. We can use them interchangeably. The x or the y in the equation each have an invisible coefficient. Ooh, that should say exponent of 1. Let's fix that. Hope you're paying attention. Exponent, not coefficient. Sorry about that. I must have just gotten typing and I typed coefficient. Invisible exponent of 1. So no x squared, no x cubed, nothing else being done to x, including no absolute value. We'll see that in a minute. So, are these linear? Are these functions linear? Please remember, we just went over it here on the previous slide. This is the same thing as saying y equals x. Same difference. These are interchangeable here. Is this linear? Well, we have x, we have y. It's first degree, so yes. That one is definitely linear. F of x equals 3x minus 8. This is linear as well. Again, I could write it. Y equals 3x minus 8. And I know it's linear because x is to the first degree. I have both my x and my y. That's going to make a straight line. The next one, however, is not. I can still write it y equals x squared, but it is not linear. So this one was a yes, and this one is a no, because it's got the squared in it. It's got that x squared. This is a parabola. Specifically, it's our basic parabola with its vertex at the origin. Looks like that. Oh, not disconnected. There we go. That's better. Next one has an x, has some numbers. Doesn't matter that they're fractions. We could still write it y equals. It is still linear. We're going to learn a whole lot more about what you can tell from a function besides what you see already with the whether or not x is squared, telling you whether or not it's a linear function. You could tell more from the placement of these numbers. Some of you might remember from last year. And this one, we could write it y equals the absolute value of x. That is not linear, because it's got the absolute value on it. To be specific, that graph is linear on both sides, but it makes a V shape, which should be easy to remember because absolute value has a V in it there with value. Okay? Not they're linear, we're going to be working on writing function rules. Sometimes you're going to be doing it from a word problem. This is something we've kind of already done, except now you've got two variables instead of one. Let's read through it. A taxi company should be charges. Let's fix that real quick. Charges $4.25 plus $1.50 per mile for rides in the city. Write a function rule for the total rate R as a function of the total miles M. And so we're also remembering here that means we're dealing with independent and dependent variable relationship. Okay, the rate depends on the number of miles. So the rate, that's your independent variable. So when we write this function rule, we're going to write R equals, the rate equals, and then it's the amount of money that you spend for a ride. So it's $4.25 plus $1.50 per mile, and the number of miles is represented with an M. So most of these linear functions are going to look pretty similar. You're going to have a constant, you're going to have a coefficient with your variable, and you're going to have your other variable. So in this case, R equals $4.25 plus $1.50 M. We can also write this as a function of M. It could be f of M equals 4.25 plus $1.50 M. Same idea. That would just be using R and f of M as the rate interchangeably. Let's try a couple more of these. All right, let me number them because my image ended up without numbers here. I think it's because it was numbers 6 through 10, and I didn't want to keep the numbers being all disjointed and jumpy. All right, let's look at number 1. The price of ice cream is $3.95 plus 85 cents for each topping on the ice cream. So the price P is equal to the $3.95 plus 85 cents. Remember your 0 for your naked decimal point per T topping. If you're getting this, no problem. Why don't you pause it and try the rest of them? If not, follow with me. The babysitter's earnings, E, are a function, so E equals. So whatever the variable is for the function, so E is a function of, P is a function of, you're going to have that variable by itself. And then on the other side, the number of hours, N, worked at a rate of $7.25 an hour. So $7.25 per N hours. So there's your function rule for number 2. Let's look at number 3. The price P of the club's membership, is $30 for an enrollment fee and $12 per week W to be a member. So we have the price P equals $30 plus $12 per week. And we remember at this point that per often means multiplication. If we say per week, per day, per hour, we're usually multiplying by the number of weeks, days, or hours in the situation. How about the last one? The plumber's fees. Gosh, plumbers can charge a lot of money because when you need a plumber, you need them. It's not one of those things you can skimp on. All right, a plumber's fees, F, are $75 for a house call plus $60 per hour worked. If I was to now say that the plumber worked for 6 hours, find the total bill for the plumbing job. Well, what would you do? Well, the total cost F is equal to 75 plus 60 times the number of hours. So plumbing, as you can see, gets super expensive. 75 plus 360 would be 435. 75 plus 360. I think that's right. Gosh, that's a lot of money. For 6 hours of work, it doesn't really seem like that much money, but I think this is probably an older example. I think it's become a bit pricier than that to have a plumber come over. Anyway, there you go, writing some function rules. Going to move on now. Let's look at writing function rules, from a table. Sometimes these are easy and straightforward, and sometimes they are not. And we did some in class that I know some of them were a challenge. Let's go ahead and look at this one. The trick we talked about in class was to look at the difference of the y's. Most of the time, your x's count by ones. Look at the difference of your y's. In this case, it's up by 3, up by 3, up by 3. Well, if that's the case in your table, use trial and error. Try starting off with 3 times x for your function rule. So 3 times x, then you have to do something to that to get the y that's there. And I'm going to use f of x. Remember, f of x and y, same diff, same thing. So 3 times 0 would be 0. So then if I was to add 5 to that, would that work? All right, let's try it on the next one. 3 times 1 is 3 plus 5 is 8. Uh-oh, I think we found it. 3 times 2 is 6 plus 5 is 11. 3 times 3 is 9 plus 5 is 14. We found our function rule. Let's try this one down here. Again, counting up by ones here on the x's, but here we're counting by 5s on the y's, by 5s. So it's probably, I'll use y this time, 5 times something with x and then something else. Well, 5 times 0 would be 0. How do I get a negative 3? Well, minus 3. Let's test that out. 5 times 1 is 5, minus 3 is 2. Yes. 5 times 2 is 10, minus 3 is 7. Yes. 5 times 3 is 15, minus 3 is 12. We got it. This last one might look tricky, but it's not. If you recall the metamorphosis video that we watched in class, your f of x or your y, in this case, is just going to be equal to always 5. Doesn't matter what x is, it's always 5. So you could have f of x equals 5, or you could have y equals 5. Either one is fine. How about a function rule? Here's my example here. Yes, you should copy it down. Here's the function rule. Y equals negative 2x plus 1. It could just as easily have said f of x equals negative 2x plus 1. The way that they wrote it out in the table is they wrote their x column, the work to get y, and then the ordered pairs x and y, and then they graphed it. So they plotted the points and drew the line. So you plug in the numbers of your choice. Notice they picked a negative, a 0, a positive, and another positive, and the numbers are rather small. You also want to think about what you have in your function rule. Let's look at our one example for this. Y equals 1/2 x minus 1, same thing as, switch to the pen, LeCompte, f of x equals 1/2 x minus 1. Now again, we got to make a table. I'm going to write my table just like they did on the previous slide with the ordered pairs to make it easier for graphing at the end. Let's change colors. So now we are plugging in our values. Now stop and think here. You don't want to pick 1 because you're going to have a fraction here. So instead of picking 1 or 3 or -1, let's make sure we have an even. And I'm going to make my first number a negative, so -2, 0, and let's do 2 and 4. And again, I only chose those because I want to get rid of this fraction. I don't want the fraction to make the numbers more complicated. Because I pick the numbers I'm plugging in for x, why not make life easy on ourselves? Half of -2 is -1, minus 1 is -2. So the first ordered pair is -2, -2. We'll graph them afterwards. Plug in a 0. 0 times a half is 0, minus 1 is -1. So 0, -1. Plug in the 2. 1/2 of 2 is 1, minus 1 is 0. So 2, 0 is on my line. And finally, 1/2 of 4 is 2, minus 1 is 1. So the ordered pair 4, 1. Let's plot those ordered pairs over here on the graph. -2, -2, right there. 0, -1, right there. 2, 0, right there. And 4, 1, right there. Not complicated. We remember how to do this. Extend the pattern out. Try to follow the same pattern all the way to the edges of the graph. Put your arrows on. We're going to learn lots and lots of ways to graph. Making a table of values like this. You're not going to do this all that often come pretty soon. You're going to have a better strategy for graphing every line I give you. All right, folks, that's it for more functions. I will see you guys next time in class.